happening.
Helps me improve my writing in real time on almost any platform I use. Now, with their premium tone suggestions, I can not only evaluate but fully adjust my tone to ensure that I always come across as intended, whether it's too friendly, formal, or not confident enough. And with apps.
Okay, we're not going to listen to that. That's ridiculous. Oh my God. Have to put ad block back on. I don't know. It must have gotten turned off or something. Okay, at any rate, skip.
We often abbreviate oxidation and reduction, so we just call these redox reactions for short.
Okay, so oxidation reduction reactions get abbreviated as redox.
So, what is an oxidation reduction or redox reaction? Here's a quick definition. In oxidation reduction reactions, electrons move between atoms.
Who moves? Electrons. So this is actually, it's kind of neat that we do this after acids and bases, because in acids and bases, protons move from one substance to another, the hydrogens move. Here, it's electrons that are moving.
Check out this diagram here. We got atom A and atom B, and there's an electron moving out of atom A into atom B. So this is definitely an oxidation reduction reaction because there's an electron moving between the atoms. Now, we can describe the movement of this electron using the words oxidation and reduction. So let's learn specifically what both of these mean. Reduction is a gain of electrons. I know this seems kind of confusing because usually when you have a reduction of something, you have less of it. We'll talk later about why a gain of electrons is called a reduction.
Okay, so reduction is a gain of electrons and oxidation is a loss of electrons.
Anyway, reduction, gain of electrons, and then oxidation, which is a loss of electrons. So we got reduction and oxidation. What's happening to atoms A and B over here? Well, atom A is giving up one of its electrons. It's losing an electron. So at atom A, oxidation is taking place. Atom B is receiving an electron. It's gaining an electron. So at atom B, reduction is taking place. Now, we can modify these words slightly to come up with terms we use to describe what's happening to the atoms. Atom A is undergoing oxidation, so we can say that atom A is being oxidized. Atom B is undergoing reduction, so we can say that atom B is being reduced. So we got.
Okay, so A is being oxidized, B is being reduced.
Oxidation, oxidized, reduction, reduced. The big picture here is that reduction is a gain of electrons and oxidation is a loss. So I don't know about you, but when I was first learning this stuff, I found it so confusing. Why should a reduction be a gain of electrons? Usually when you're reducing something, you're getting less of it. So here's one thing that might be helpful to think about. That's that electrons have negative charge. So as you add electrons to something, its charge goes down. The more electrons you add, the lower the charge. So as you add electrons, as electrons are gained, the charge reduces.
Okay, so as you add electrons, as electrons are gained, that's in that little box there, the charge is reduced. The charge reduces as you gain electrons. Okay?
So that might be helpful to keep in mind to have this make a little bit more sense. Still, these things can be really confusing to remember. So here are a couple really great mnemonics. First is the term oil rig. This is the name of one of those big structures you use to drill for oil. OIL stands for oxidation is loss, and RIG stands for reduction is gains. This is a really good mnemonic. Here's another one you might like if you like animals. Leo the lion says grr. All right? LEO stands for loss of electrons is oxidation, and grr stands for gain of electrons is reduction.
Okay, so we have oil rig, oxidation is loss, reduction is gain. I, like Leo the lion, says grr. We even have a cute little lion on the page for you. So loss of electrons is oxidation. Gain of electrons is reduction. Leo the lion says grr.
So learn one or both of these. They'll be a great way that you can always remember what reduction is and what oxidation is. Okay, oxidation and reduction happen in all sorts of chemical reactions. They're like the super important thing that makes those reactions happen, that makes them go. So to learn more about this stuff, we're going to have to look at an example of a chemical reaction where oxidation and reduction are taking place. Here's a chemical reaction that we're going to be talking about. Sodium and chlorine coming together to make sodium chloride, table salt. Now, sodium chloride is an ionic compound, which means that it's made of ions. Specifically, the sodium 1+ and the chloride 1- ion.
Now, before we get to the product, what are the charges on the Na and the Cl in the reactants? There's no charge. Any element in its elemental state, its charge is 0 because it hasn't given away electrons to anyone or taken electrons.
Ions. These two ions stick together because they have opposite charges, and opposite charges attract. Now, Na and Cl, they didn't always have charges though. Over here, before they combined, they have no charge. They are two electrically neutral atoms. So in order to come together and make sodium chloride, these two atoms have to end up getting charges, and then they stick together. So let's talk about how this happens, how they end up getting charges. So we start out with Na and Cl here as electrically neutral atoms with no charge, and they're on their own. They're separate. The next thing that happens is sodium gives one of its electrons to chlorine. So this is where the charges come in.
So who is being oxidized? Na, because it is losing electrons, which is oxidation. LEO, losing electrons, oxidation. Sodium lost an electron, oxidation. Chlorine, what did it do? It gained an electrons, and gaining electrons is reduction. GER, G-E-R, okay?
Sodium loses one of its electrons, so it becomes Na+1. And chlorine gains an electron, so it becomes Cl-1. Now we have two ions with opposite charges. What do oppositely charged things do? They stick together. So these two ions come together and they stick, making sodium chloride.
Now, just before we go on, do you remember how reduction is the reduction in charge? Okay, so you can see how the chlorine went from being 0 to being -1. The charge got lower. Yeah, 0 to -1, the charge got reduced. So chlorine was reduced.
Okay, so this is the process where we start from electrically neutral atoms. We have an electron transfer, we get ions that then stick together. So here's the equation that I showed you earlier that describes this process. There are a couple things that I could add to this though to make stuff a little clearer. Check out these numbers that I've written in here in the red. These are called oxidation numbers, and they give me a sense of what's happening with the electrons and with the charges.
Oxidation numbers, for now, you can just think of them as charges. They're a little more complicated because we assign oxidation numbers to atoms within covalent compounds, and they don't really have charges, but they're kind of like charges. You can think of oxidation numbers as being like charges.
So above Na and Cl, I've written zeros. That indicates that these two atoms start out being electrically neutral. They have no charge. That's what the 0 means. Then on this side of the equation, once the sodium and chloride have taken on charges, I put those charges above each element. +1 for the sodium and -1 for the chloride. These oxidation numbers help us keep track of how charges change during a reaction. Most importantly for this reaction, they remind us that sodium and chlorine start out neutral and only end up getting a charge later after this electron transfer takes place. So, that is oxidation numbers, and we'll talk more about those in coming lessons. So, obviously, this is an oxidation-reduction reaction because there is a transfer of an electron between these two atoms. I now want to describe what's happening to sodium and chlorine using these terms reduction and oxidation. So, just to refresh your memory, reduction here is a gain of electrons, and oxidation is a loss of electrons. So, for sodium, what's happening? Is it being reduced or is it being oxidized? Well, sodium is giving up one of its electrons, it's losing an electron, so it's being oxidized. Here's a diagram of sodium giving up that electron. Now, chlorine, on the other hand, is receiving an electron. It's gaining an electron, so chlorine is being reduced. So there's oxidation and reduction going on here. We can sort of show this oxidation and reduction with this picture that I drew, or we can describe it in words. The next thing that I want to do is I want to show you how we can write chemical equations that show oxidation and reduction. So let's start out here with chlorine. I want to write a chemical equation that shows the reduction of chlorine. So I'm going to start out with Cl here. This is neutral chlorine. It doesn't have any charge. It's this thing here. And then it receives an electron. So to write an equation for that, I'm going to write plus E minus. E minus is a symbol we use for electrons. So Cl, neutral chlorine, plus 1 electron gives me this guy right here, Cl 1 minus. So this is the equation for the reduction of chlorine, for chlorine gaining this electron here. Okay, now for sodium things are a little bit trickier for the oxidation. Let me show you why. So what I really want to write is Na minus 1 electron gives Na 1 plus. But unfortunately, I can't.
Do we ever write negatives in our chemical equations? Do we ever subtract things? No. So how could you rewrite that so that you no longer have minus an electron? What would you do with that electron? Yeah, you're going to put it over into the product, okay?
Can't write this because in chemical equations, we can't use minus signs. We can only use plus signs. So I can't write the oxidation like this. Instead, I'm going to write it like this. I'm going to start out with Na here, and then I'm going to put my arrow. So Na turns into Na1 plus 1 electron. Writing the electron on this side of the equation indicates that it's being spit out, that Na is losing it. It's no longer part of the atom. So to write reduction, we put the electron on this side of the equation because it's coming together with the atom. To write oxidation, we put the electron on this side of the equation because it's getting spit out. So
you should be able to recognize an oxidation by the fact that an electron is coming out, so electron is lost. And you should be able to recognize a reduction because the electron is being gained, okay? And you can also notice that in reduction, the charge has gone from 0 to -1. The charge has gone down. In oxidation, the charge goes up. Or actually, I suppose I should use the correct term. The oxidation number goes up.
These are the reactions for oxidation and reduction of sodium and chloride. Now I want to talk a little bit more about these two reactions and how we can combine them to make a larger, bigger picture equation. Here's our big picture reaction for sodium and chlorine coming together to make sodium chloride. Now, this reaction here really has two processes going on within it. One of these processes is the oxidation of sodium. It starts out at 0, loses an electron, and becomes sodium 1 plus. And here is the equation for just the oxidation. The other process that's going on in this reaction here is the reduction of chlorine. Chlorine starts neutral at 0, it gains an electron, and it ends up as Cl1 minus. And here is the equation for the reduction of chlorine. Now, these two equations down here are called half reactions. They show...
Why do you think they're called half reactions? Because they're half of the overall reaction. Yes, but it's nice to be able to separate them out because it allows you to see what's happening with the electrons. Plus, later on when we get more complicated ones, separating out half reactions makes balancing the equations much easier. And you're going to learn how to balance some tricky equations this year that you would have had a lot of difficulty with last year when you were just trying to do it by putting coefficients in front randomly. Yeah?
Either oxidation or reduction, and they're called half reactions because they each kind of tell half the story. You put them together and you get the big picture reaction that shows both oxidation and reduction. So for every oxidation reduction reaction like this one, you can write two half reactions, one for the oxidation that takes place and one for the reduction that takes place. Now, it's super important to keep in mind that oxidation and reduction always have to happen together. They always have to happen at the same time. Because if one atom is gaining an electron, that electron had to come from somewhere. So another atom had to give up that electron. You can see that right here. The electron here that chlorine is gaining is the same electron that sodium was releasing. So oxidation and reduction always have to happen at the same time. They always have to happen in parallel. You can't have reduction without oxidation. You can't have oxidation without reduction. So that's an introduction to oxidation reduction or redox reactions. We learned that...
Okay, that's enough of that. And we're going to go on to this next little bit here. Let's get the link.
Here's an example of a really common question that a lot of students get wrong. I want to make sure that you don't. This is a great test of how well you understand oxidation and reduction. So here's a question. Does the following chemical equation, this chemical equation right here, represent an oxidation reduction reaction? So
you tell me, does it? Does this equation represent an oxidation reduction reaction? What's the oxidation number of K on the left-hand side? It's got a +1 charge, so the oxidation number is +1. What's the oxidation number of K over here? It's part of a compound. What's the charge of K when it's in a compound? +1. So the oxidation number over here is +1. The oxidation number over here is +1. How about chloride? Over here it is -1. Over here the oxidation number is -1. Has anyone lost or gained electrons in this process? No, there's been no change of oxidation number, so there's been no thing. Do we need to go through that? Oh well, let's just, should we put him on fast forward? Okay, let's put him on speedy play. Let's put him on 1.5. Okay, there we go.
So is this an oxidation reduction reaction? You can think about this for a minute, pause the video, and then we'll talk. So what do you think? Is this an oxidation reduction reaction? Well, most people say yes, it is. But actually, the correct answer is no, this is not an oxidation reduction reaction. So if you got this wrong, I'm not a professional mind reader, but I want to try to read your mind right now and guess why you thought this was a redox reaction. I'm guessing it's because you saw the plus and the minus, you saw these charges here, and you realized we were dealing with ions, and you thought, yeah, pluses, minuses, charges, ions, these are things that we see in oxidation reduction reactions. Well, you're half right. We do see those in oxidation reduction reactions. But just because an equation or a reaction has charges and ions doesn't mean that it has to be an oxidation reduction reaction. Remember what these two words mean. In order for something to be an oxidation reduction reaction, we have to see electrons transferred between atoms. That's not going on here, and let me show you how I know that. So KCl here is an ionic compound which means that it's made of ions, the K plus ion and the Cl1 minus ion. So these atoms have charges, and we can even write numbers above these atoms to reinforce what charge they have. 1 plus for the K, 1 minus for the Cl. Now, over on this side, let's take a look at what's going on. For this to be an oxidation reduction reaction, the K and Cl would have to have a transfer of electrons that create these charges, the plus and the minus. But the atoms over here, they already have charges, right? K plus, here's a picture of the atom. Cl1 minus, here's a picture of the atom. And I can put these numbers above them. Got 1 plus for K, 1 minus or minus 1 for Cl. So the point of this equation here is that the charges don't change. K and Cl start out plus and minus, and they end plus and minus. There's no transfer of electrons that takes place. The only thing that happens is two atoms that started out charged end up sticking together. That's the only thing that's going on in this equation. Now, if this still is a little bit confusing, let me show you how we could change this equation to make it actually an oxidation reduction reaction. And then when you see the differences, I think this will all make sense. So here's the equation that we said was not a redox reaction. Here's an equation that is a redox reaction. These two reactions look pretty similar, except for one important difference.
What's the important difference? There's no charges over here. Yes, do you think you could fill in the little boxes above the K and the Cl?
Take a look at how K and Cl start out. In this equation up here, they had charges. In this equation down here, they don't have charges. They start out not as K plus and Cl minus, but as neutral atoms, as K and Cl. To emphasize that they're neutral, we can put these oxidation numbers, these zeros, above them. The zeros tell us that they're neutral. And then just like before, KCl is an ionic compound with K plus and Cl minus. Here are the charges for those atoms. So, in order for K and Cl to become K plus and Cl minus, there has to be a transfer of electrons. So what happens is K, potassium, gives up one of its electrons. It gives it to Cl. K loses one of its electrons to become K plus or potassium 1 plus. Cl gains one of these electrons and becomes Cl minus, chloride. So now these two atoms end up with charges.
Okay, so I'll give you a second to draw that little arrow with the electron. If you haven't already done so, there's a box where you can show the transfer of the electron. Are you okay? Okay.
But only because of a transfer of electrons. That transfer of electrons caused potassium, K, to become oxidized, and it caused Cl, chlorine, to become reduced. So that's why this is an oxidation reduction reaction, because potassium and chlorine, K and Cl, start out neutral. There's a transfer of electrons which gives them charges, and then those charges stick together.
Yes. It starts out neutral. It starts out with the atomic number of potassium is 19. So it has 19 protons, 19 electrons. Yeah, neutral. It gives away an electron, so it still has 19 protons, but it's given away an electron, so now it only has 18 electrons, and that's why it becomes positive. Did that make sense? Maybe not. So you start with 19 positives and 19 negatives. When it gives away the electron, now it has one less negative than positive, so the net charge is +1. Is good? Okay, cool.
The reason why this here was not a redox reaction is because potassium and chloride started out already with charges. So we didn't need this transfer of electrons to give them the charges. So if you ever run into a question like this, remember, just because an equation has pluses and minuses doesn't mean that it's an oxidation reduction reaction. For something to be an oxidation reduction reaction, you've got to see a transfer of electrons. This equation wasn't a redox reaction because there was no transfer of electrons. Two things that started out as +1 and -1 just stuck together. They were still +1 and -1 at the end. This equation, though, it was a redox reaction because these two things started out neutral, K neutral and Cl neutral, and the K got oxidized to 1 plus by losing an electron. The Cl got reduced to 1 minus by gaining an electron. The charges changed because electrons were transferred, and that's why this is a redox reaction.
Is good? Okay. So now you have the general concept. we are going to learn a tool in our toolkit for oxidation and reductions on page 5. We're going to learn how to find oxidation numbers. Some of them are really easy. Some of them are a little more complicated. Okay, so we're going to move on to page 5. How to find oxidation numbers. So oxidation numbers are kind of like the charge on an atom. So for example, as we saw on the little video, if we have Na with nothing up here, the ON, which stands for oxidation number, is 0. If we have an Na with a plus charge, the oxidation number is +1. And if we have the O here in Na2O, you just have to say, well, what's the charge of oxygen in an ionic compound? It is, oxygen is 2-. Yes? So the oxidation number is -2. And if you've forgotten how to tell what charge your ions are, if you go to your data pages, we've got our table of common ions. Oh, look, it is so kind to tell you that oxide is -2. Yes? Or you can go to your periodic table and you can say, oh, look, I know that everything in column 16 is going to have a -2 charge because it's got 6 electrons in its valence shell. How many is full? Valence shell is full with 8. So it would need to gain 2 electrons, which means it has a -2 charge. But it is listed for you in the table of common ions if you forget. Okay, so we can also find oxidation numbers for atoms that are bonded covalently and don't actually have charges. Okay, so an oxidation number is not really a charge, but it's kind of like a charge, but we just kind of pretend. Okay, so the oxidation number of carbon in C2O4, 2- is +3. And you might say, how on earth did you do that? And I will say to you, that's okay, we're going to learn how in just a moment or two, okay? The oxidation number of carbon in C3H8 is -8/3. Yes, you can have fractions. All right? So in order to be able to figure out these more complicated ones, like what the heck is carbon and C2O4 2- and what is carbon? Why do I get an 8/3? That's crazy, man. We're going to need to learn some general rules. So you need to memorize these. Pure elements. What is the oxidation number of any pure element? 0. Okay, so any lone element, any pure element has an oxidation number of 0. So those are pure elements. In compounds, what's the oxidation number of all the alkali metals? That's column number 1. It is 1+. Always. There's no exceptions. The alkaline earth metals, group 2, are always +2. You guys knew that, yes? And these are listed in order of priority, okay? Alkali and alkaline earth are always +1 and +2. There's no exceptions, or +1, yeah. Hydrogen has an oxidation number of +1. There's one exception, which we'll come to in a moment. Oxygen has an oxidation number of -2. Does this make sense to you? Hydrogen ions are +1. Oxide ions are -2. So they're nothing new and different, right? Oxygen also has one exception. And what is the charge that you would find in of a halogen? Halogens are always -1. Now, fluorine will always be -1. Chlorine, bromine, and iodine have many exceptions, but those are fairly rare. Okay? So here are our exceptions. The exceptions. Remember, hydrogen is almost always +1. But if we have the hydride ion, hydride is H-, it has an oxidation of -1. And you'll recognize it because you'll have, for example, NaH. Now, what do you remember about alkali ions? Alkali ions are always +1. Yes? This is a neutral compound. So what does hydrogen have to be? It has to be -1. Okay? Don't go looking for hydrides. They're very rare. Okay? And don't go looking for hydrides in covalent compounds. They're always with metals. Okay? The hydride ion is always with a metal. And the metal will have the positive charge, which means the hydrogen has to have taken an electron. Oxygen's exception is the peroxide ion. Okay, peroxide looks like this. We have an oxygen with a negative charge bonded to a second oxygen with a negative charge. So overall, that thing has a 2- charge. So each oxygen, though, is -1. Yes? Can you think of a peroxide compound? Probably heard of one. Hydrogen peroxide. Sold at your local drugstore. Hydrogen peroxide is H2O2. You'll recognize a peroxide because it will look like a normal compound, except for there will be an extra oxygen. What would the normal compound be, the more common compound be for hydrogen peroxide? H2O, right? It's almost water, but it's got an extra oxygen. Yeah? Another one we might have is Na2O2. That almost looks like a regular compound. What would the regular compound be? Na2O, because normally oxygen is just 2- Na2O. So that's almost Na2O, but not quite. Yes? So as I said, don't go looking for peroxides and see them coming like out of the corner everywhere. There's very few peroxides. There's hydrogen peroxide, and then there's metal peroxides. And you'd have to look and just say, oh, it's an O2. Don't look for them in organic compounds or covalent compounds. You won't find them. Okay? A peroxide is only inorganic. These are with a metal or H. And you have to look and say, is it normal oxygen or is it that O2 peroxide? Right? The ionic compounds that look strange, Na2O2, what's up with that? CaO2, what's up with that? H2O2, Peroxide is an ion. It will never occur in covalent compounds. All right. So finding the oxidation number of an element in a compound. So we're going to have, excuse me, NH4Cl. And I'm going to do it over here. So if you would like to work through it with me, you can grab yourself a piece of paper, or you can follow along in the book. It doesn't matter to me. And we are looking for the oxidation number of the N. Okay? So the best way to do this is to be very systematic about it. You can do it in your head when you get good at it, but it's an easy way to make stupid mistakes, especially if you're dealing with like thirds or something like that, okay? So what you do is you say, I have one N, I have 4 hydrogen, and I have 1 chlorine. And then what I do is I look up at my top corner here and I say, what is the charge, the overall charge? Is there anything up there? No. So that's good. The overall charge is 0. So when I take 1 nitrogen, 4 hydrogens, and 1 chlorine, my overall charge equals 0. Okay? We are solving for the 1 nitrogen, so we're just going to leave it there. So we're going to have 1 nitrogen. But now we're going to substitute in those numbers that we remember for the oxidation number of hydrogen. What is the normal oxidation number for hydrogen in a compound? +1. Okay. And then we have 1 chlorine. What's the oxidation number for chlorine in a compound? -1. Okay, and now we just add up. We still have 1 nitrogen. Now we have +4, and -1 gives me +3, and that still equals 0. And so my 1 nitrogen has a charge of -3. So the oxidation number of nitrogen is -3. Does that seem straightforward enough? Okay, it's just a little bit of algebra. I mean, honestly, the first section of this is quite nice. Thank you. Yes. Fun. Okay, who's our next example? CO3 2-. Okay, so we write out all of our atoms. We have 1 carbon. We have 3 oxygens. And so 1 carbon plus 3 oxygen gives us our overall charge. And in this case, the overall charge is equal to 2-. We're looking for the oxidation number of carbon, so we're just going to leave carbon alone. We have 1 carbon plus 3 times, what's the oxidation number of oxygen? -2 equals, you can write 2- or -2. It doesn't matter as long as you don't get too wound up about it. I'm going to write -2 just for now. And then, so we now have 1 carbon -6 is equal to -2. So 1 carbon is equal to +4. Do you need to write that positive? Yes. Okay, for oxidation numbers, you need to include a positive when it is positive. Okay. And now we're going to get into one of the examples of a goofy one. C3 H2O2. And we're going to find the oxidation number of carbon. So we have 3 carbon plus 2 hydrogen plus 2 oxygen equals 0. And I like to put a line through my 0 so it doesn't look like an oxygen. Okay, and sometimes I even like to leave a big space in between my 2 and my oxygen so that it doesn't look like a 22 oxygen. Okay, but it just depends on how hard of a time you have keeping track. So 3 carbon plus 2 times what? Positive 1. Because remember, hydrogen is not going to be -1 unless it's a hydride, which is sort of special. And 99% of the time, it's not going to be special. Okay. And then we have 2 times oxygen. Oxygen's oxidation number is -2. So we have 3 carbon plus 2 minus 4 equals 0. So 3 carbon, you don't have to show all this work. You can do some of it in your head if you prefer. I'm just going to write it out so you don't get confused watching me do it. So we have 3 carbon minus 2 is equal to 0. So 3 carbon is equal to positive 2. So carbon is equal to positive 2/3. So the oxidation number of carbon is positive 2/3. Is good? Okay. If you are finding the oxidation number of a multivalent metal, where would we find multivalent metals? Multivalent means they could have more than one charge. Where do you find metals that have more than one charge on your periodic table? You don't know? In the middle, okay? And a few over here, right? You're like, okay. I just don't know the charge of them, all right? So if we have something like this, Pb, NO3, 2. Now, if we actually look on our data pages for lead, you can see that we have lead 4+ and we have lead 2+. Yes, those are the 2 most common charges of lead. By the way, I want you to make sure that you understand this list here are common ions. Some of them have lots of other different charges. So if you're like, ooh, manganese can only be +2 or +4. No, manganese can be +6, +5, +7, +1. Manganese has like 1 billion different possible charges. Okay, so don't use this chart as like the be all end all, like these are the only ones. These are just the common ones. All right. But if we go back here, sometimes people get to this one and they're like, well, I know oxygen's oxidation number, but I don't know nitrogen's. How am I going to solve for lead? Whoa, that was exciting. Do you think you could find the oxidation number of lead? Probably my grade 9s could find the oxidation number of lead. because they don't know any better. They wouldn't be thinking too hard. The only reason you wouldn't be able to do is if you're thinking too hard. Oh, what's the charge of nitrate? That's a good question. NO3 is -1. So yeah, so lead is going to be 2+, because if you have a polyatomic ion, you can say I have 2 NO3 minuses. So my negative charge is -2, so then my lead must be 2+. Okay, so it's just like finding the charge of those ions when you were in grade 9 trying to write the chemical name with the Roman numeral. Okay, so that's the only other thing there. And what time is our class over today? It is over at 48? 46. 46. So we have about 10 minutes left. Why don't you do some of the oxidation number questions, and then your homework for the weekend will just be to do your practice quiz and study for your test. Okay, but you'll get a little practice on oxidation numbers right now. Okay, so just do some of those. If you're feeling fancy, you can start with some of the later ones. Just pick a few that look crazy. Yeah, for sure. Did everyone get the answer key for the practice quiz? Yes? Okay, good. Let's make sure you got one. Good. Yeah. Practice quiz answer key. Yeah. Yeah. Over that side. Oh, it's because you got potassium hydroxide. I mean, you can order if you want. Order for but it would be like something compound. So like, if it's really yeah. I don't know what you were getting complicated with what you were doing. I think it was just so high, trying to think of maybe the high. Wrong. Okay, so stop doing that. Just interpret it rightly. Okay. Hi. Okay. 5.1 yes. Yeah. Okay. Well, if you can do yeah. Actually, no. Yeah. Well, so don't forget about like pages 20, 21. We sort of like got there, and yeah. So don't forget pages 20, 21. They are testable. So do give them a try over the weekend, okay? Mm-hmm. Goes from 0 to +1, and scale those pieces up to the -1 there. It's because the charge is changed. It could go the other way around, but I think it's 0. But the quarter charge changes one side with different whereas here it stays the same. Okay. Yeah. Starts as neutral. Yeah. Or protons and electrons. Yeah. Of course. Yeah. They do, but the compound is neutral, right? Once they're together, that's neutral. So that takes care of the neutrality. And the electron is more stable on the chlorine than it is on the potassium. Yeah, yeah. Yeah, to become more stable, it gives an electron chloride, and then the two of them stick together, which makes the whole thing. Yeah, yeah. Uh-huh.
So the charge is like
Is S one of the rules? Is S in the rules? No, no sulfur. So you don't know sulfur. So what are you gonna do? Oh. What about sulfate? SO4.
Ah.
Oh. Oh. Do you know the charge of sulfate? Yeah. Yes. Yep. Yeah. Yeah. No, you don't have to. No. Like you would say, I put these species together, and then my equilibrium would be HCN plus H2O in equilibrium with CN. So, yeah. Yeah. No, you don't have to do it on a piece of paper. No. If you can just find them, you're good to go. Okay. Yeah, that makes sense, right? You can get as much work as you want. Okay. So anything higher than 5.4. Okay. So big chemistry weekend this weekend, right? Oh. Yeah. Yeah. Everything about that.
He's so cool. Oh, that's so blood. So like even though like it has like
I just thought that's me.
Wow, okay.
So 3 only picks you up in 7s.